Now, in this lecture, we'll find out the radius of the small circle. In the drawing, we have this small circle that is inside a semicircle. We know that side CD, line segment CD equals to 4 units, line segment DB equals to 4 units, angle CDB, this angle equals to 90 degrees, and we want to find out the radius of this small circle. So first of all, we will do a construction. We will complete this semicircle to a circle. So we completed the semicircle to a circle, and in the next step we will extend line segment CD by a straight line until it touches the circle, and we will define the touching point of the extended line segment CD and the circle as point E. Actually, we know that CD is a straight line. CD is a straight line, and when we extended the straight line CD by a straight line, the result must be a straight line. That is to say, when you extend a straight line by a straight line, the result must be a straight line. Therefore, when we extended the straight line CD by a straight line, we got line segment CE. That is the result. So that it must be, so CE is a straight line. So we can write down that CE is a straight line. Line segment CE is a straight line. And we have the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles at point D on this side of CE must be equal to 180 degrees. So which angles we have at point D? We have here 90 degrees and angle EDB. So 90 degrees plus angle EDB, in total they must be equal to total to 180 degrees, according to the rule that I mentioned, that the sum of the angles on one side of a straight line is equal to 180 degrees. Okay. So here we will subtract 90 degrees from this equation, and we get that the missing angle EDB, is equal to 180 degrees minus 90 degrees, it is 90 degrees. Okay. Angle EDB equals to 90 degrees. This angle is a right angle, it is equal to 90 degrees. Okay? And actually, when we extended the semicircle to a circle, we actually created the mirror image, we created the second semicircle that is a mirror image of the original semicircle. So this semicircle is the mirror image of the original semicircle, and then we extended line segment CD by straight line and created line segment ED. We know that angle CDB equals to 90 degrees. Angle EDB also equals to 90 degrees. That is to say, actually, DE is a mirror image of CD. And because of the fact that DE is a mirror image of CD, DE must be equal to CD, but it will be in the opposite direction. Okay, exactly like when you look at when you look at the mirror, you see yourself in exactly in the same direction, exactly in the same dimensions that you are, but in the opposite direction. The same thing is true here, that because of the fact DE is the mirror image of CD, you can write down that DE equals to CD. DE equals to CD, and the only difference between those two line segments is between their directions. One is the opposite direction of the other. So because of the fact that DE is the mirror image of CD, therefore CD equals to D equals to CD by symmetry. Okay, but it is given us in the question that CD equals to 3 units. We know that CD equals to 3 units. So from this equation, 3 equals to CD equals to DE, we will derive that DE is also equals to 3 units. Okay, DE equals to 3 units. Okay, so if we write here that DE equals to 3 units, in the next step, I'll present to you a new rule, which will be rule number 1. According to rule number 1, if two chords intersect with each other inside the circle, then the following equation is true. AO times OB equals to CO times OD. So I write it down. If two chords intersect with each other inside the circle, then the following equation is true. So we actually have this circle, and inside this circle we have two chords. This is called AB. This is called AB. And this is called CD. Repeat again, this is called AB, this is called CD, and those two chords intersect with each other. At this point, we define it, the intersection point is point O. So if this is the data that has been given to us, then according to rule number 1, we get that the following equation is true, that AO times OB AO times AB equals to CO times OD. I repeat again, if chord AB intersects with chord CD at point O, then the following equation is true, that AO times OB equals to CO times OD. Okay, so actually we can implement rule number 1 in our drawing. Why? Because in our drawing we have chord AB. This is chord AB intersects with chord CD. Chord AB intersects with chord CE at point D. Point D is the intersection point between those two chords, AB and CD. So I write it down. Chord AB, this is called AB. Intersects with chord CE. This is called CE. point D is the intersection point of chord AB with chord CE. I'll repeat again. Chord AB intersects with chord CE at point D. Point D is the intersection point between chord AB and chord CE. So all the requirements of rule number 1 are met. Therefore, we can implement rule number 1 in our drawing. According to rule number 1, we get that AD times DB, AD times DB again, AD times DB equals to CD times DE. According to rule number 1, of course, I will repeat again. Here, according to rule number 1, we get that AD times DB equals to CD times DE. Okay? So here, AD is the missing line segment, so we leave it as it is. AD times DB. DB equals to 4 units according to what is given as the question, so we'll substitute DB by 4. And it is equal to CD. CD equals to 3 units according to what is given as the question, times DE. DE also equals to 3 units. So here we found out that AB times AD times 4 equals to 3 times 3. 3 times 3 is 9, so I'll write it down. So here 9 equals to 4 times AD. So here we'll divide this equation by 4, and we get that AD equals to 9 over 4. AD equals to 9 over 4. Right here on the drawing that AD equals to 9 over 4. So we know that the diameter of any circle is twice as long as the radius. First of all, we know that here AB is the diameter of the circle and also the diameter of the big circle and also the diameter of the semicircles. Okay, and the diameter is twice as long as the radius. So if we divide the diameter AB into 2, AB over 2, it must be equal to the radius of the big circle and also the radius of the semicircles. We will define the radius of the big circle as capital R. So AB will be equal to capital R. And what is the value of AB? from the drawing, it is very easy to see that AB equals to AD plus DB. AB equals to AD plus DB. All divided by 2. Okay. R equals to AB over 2, and it is equal to AD plus DB over 2. We have already found out that AD equals to 9 over 4. So we substitute AD by 9 over 4. So AD equals to 4 over 9. And DB equals to 4 units according to what is given as the question. So in conclusion, we found out that AB over 2, that is equal to the radius of the big circle, it equals to 9 over 4 plus 4. Here we will multiply 4 by 4 and then we will divide it by 4 in order to have a common factor with 9 over 4. And we get here that 9 plus 4 times 4 is 16, all divided by 4. Okay, and 9 plus 16 is 25. 25 over 4. 25 over 4, we have to divide it by 2, of course, because it is AB over 2. So it is 25 over 4 times 2, that is 8, so it is 25 over 8 units. So we found out that capital R equals to 25 over 8 units. Okay, the radius of the big circle, that is also the radius of the semicircles, is equal to 25 over 8 units. In the next step, we will define the center of the big circle, that is also the center of the semicircles. We define the center as point P, and we define the center of this whole circle as point Q. Okay. In the next step, we'll define the point of tendency of tangent CD with this small circle as point O. And we also will define the point of tendency of tangent DV with this circle. Again, point O is the point of tendency of tangent CD with this whole circle, and we will also define the point of tendency of this tangent DB with this small circle as point M. And here, from the center of the circle, of the small circle, that is to say from point Q, we draw perpendicular to the radius I repeat again, from point Q we draw the radius QO that is drawn to the point of tendency. First of all, QO is the radius of the small circle because of the fact that it starts from the center of the circle, that is to say from point Q, and ends at point O, that is a point on the circle itself. So therefore QO is the radius of the small circle, so we define the radius of the small circle as R, small r. So QO equals to small r. And if we have the radius QO of this small circle that is drawn to the point of tendency, that is to say the radius QO is drawn to point O, that is the point of tendency of this tangent with the circle, and whenever you have a radius that is drawn to the point of tendency, then the tangent will be perpendicular to that radius. In this case, the tangent TC will be perpendicular to the radius OQ. TC is perpendicular, DC is perpendicular to OQ, that is to say, this angle will be equal to 90 degrees, and this angle will be also equal to 90 degrees. So whenever we have a radius, like in this drawing, the radius QO, it is drawn to the point of tendency, that is to say it is drawn to point O, that is the point of tendency of tangent DC with this small circle. So whenever you have a radius that is drawn to the point of tendency, then the tangent here DC will be perpendicular to the radius OQ. If this is perpendicular to OQ, it means that this angle equals to 90 degrees and this angle will be also equal to 90 degrees. Okay? So we know here the point M is the point of tendency of tangent DB with this small circle. Okay, so from point Q, that is the center of the small circle, we draw the radius QM that is drawn to the point of tendency. That is to say, the radius QM is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tangent DB will be perpendicular to the radius MQ. Again, tangent DB perpendicular to the radius MQ, that is to say, this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. Okay. So actually, I found out that in quadrilateral OQDM we have 1, 2, 3 right angles. I will write it down. In quadrilateral OQDM So in quadrilateral OQDM, we have three right angles. One, two, three, and the sum of the right angles is 90 times 3 is 270 degrees. So in quadrilateral OQDM, we have three right angles that the sum of them is 270 degrees. So 270 degrees plus the size of the fourth angle, that is actually this angle OQM, this angle. In total, the sum of those four angles must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. Okay, here in quadrilateral OQDM, the sum of angles is 90 degrees, and 90 degrees times 3 is 270 degrees, plus the size of the fourth angle. In total, they must be equal to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So if we subtract 270 degrees from this equation, and we get that the missing angle OQM, equals to 360 degrees minus 270 degrees, it is 90 degrees. So the missing angle OQM equals to 90 degrees. So actually, we found out that all the angles inside quadrilateral OQDM and right angles, they are equal to 90 degrees. Therefore, we can define quadrilateral OQDM as a rectangle. Okay, we will relate to quadrilateral OQDM as a rectangle because of the fact that all of its angles, they are equal to 90 degrees. So quadrilateral OQDM is a rectangle. Okay, but we know that the opposite sides of a rectangle are equal to each other. So here, an rectangle OQDM, its opposite sides, they are equal to each other. That is to say, OQ equals to DM. OQ equals to DM according to the rule that the sum of the angles, again, OQ equals to DM side OQ of rectangle OQDM equals to sine DM. According to the rule that the opposite sides of a rectangle are equal to each other. But we know that OQ equals to R. It is equal to R. This is the radius of the small circle. This is to say it is equal to small r. So from this equation, r equals to OQ equals to dm. We derive that dm is also equals to r. Okay, dm equals to r, it is the radius of small r, that is the radius of the small circle. Here we can write down that dm equals to r, that is the radius of the small circle. And what is the length of the small line segment dp? In the drawing, it is very easy to see that this line segment dp equals to db minus pb. db minus pb equals dp equals to db minus pb. Okay. Yeah. dp equals to db minus db minus pb again. dp equals to db minus pb. Okay, dp equals to db minus pb. So dp equals to db, that is 4 units according to what is given as the question, minus pb. What is pb? pb is the radius of the big circle because of the fact that line segment pb starts from the center of the circle and ends at point B, that is a point on the circle itself. Okay, so PB equals to capital R. So in conclusion, we found out that dP equals to 4 minus capital R. So dP equals to, we already found out that capital R equals to 25 over 8, so we substitute capital R by 25 over 8 and we get that dP equals to 4 minus 25 over 8. That is the radius of the big circle. So here we have 4 minus 25 over 8. Here we will multiply 4 by 8 and we will divide it by 8 in order to have a common factor with 25 over 8. So dP equals to 4 times 8 is 32 minus 25 over 8. Okay, 32 minus 25 is 7. So in conclusion, found out that df equals to 7/8. dp equals to 7/8. Okay, dp equals to 7/8. You can write here that dp equals to 7/8, and what is the length of that segment PM? From the drawing, it is very easy to see that PM equals to dm minus dp. Again, the length of that segment PM is equal to dm okay, so PM equals to dm minus dp. I'll repeat again, dm equals to dm minus dp. We've already found out that dm equals to small r, it is the radius of the small circle, is equal to the radius of the small circle, that is to say it is equal to small r minus dp. We've already found out that dp equals to 7/8. So in conclusion, we found out that that PM PM equals to R 1/7/8. PM equals to R 1/7/8. Okay. In the next step, I will present to you a new rule. That is actually rule number 2. According to rule number 2, if two circles have an internal notch between them, if two circles have internal notch between them, again, if two circles have an internal notch between them, two circles have an internal length between them, that is to say, the two circles touching each other internally. Here, the small circle is located inside the big circle, and those two circles have an internal length between them at this point. We define the point of tendency of the internal launch point is point S. So, the launch point, okay? It is the launch point of the two circles. We can define point S also as the point of tendency or the point of contact or touching point of those two circles. Okay, so here I wrote that S, it is the launch point. It is the point that the two circles touch each other internally. Okay, so according to rule number 1, and according to rule number 2, if two circles have an internal launch between them, and then the straight line that connects their centers the straight line that connects their centers passes through the launch point. Again, if two circles have internal launch between them, then the straight line that connects their centers passes through the launch point of the two circles. So actually, according to rule number 2, here we have those two circles have an internal launch between them at point S. Why? Because the small circle is located inside the big circle, and those two circles are touching each other internally at point S. Point S is the launch point. Therefore, according to rule number 2, the straight line that connects their centers, that is actually PQ. This is the straight line that connects their centers together. Why? Because P is the center of the big circle, Q is the center of the small circle. And the straight line that connects their centers together is PQ, and according to rule number 2, this straight line PQ that go in the red color passes through the launch points. That is to say, it passes through point S, that is the launch point. That is the point of tendency, or the touching point between those two circles. Okay, so actually, according to rule number 2, points P, Q, and S are located on the same straight line. Okay, in our drawing, according to rule number 2, points P, Q, and S, all of them are located on the same straight line. According to rule number 2, points P, Q, and S are located on the same straight line. Or we can say also that line segment PQS is one straight line. Okay. Okay. Here, line segment PQS in the red color is one straight line. Okay. So here, what is the definition of segment line QS? Q is the center of the small circle. S is a point on the small circle itself. This is exactly the definition of a radius. That is to say, QS equals to small r, that is the radius of the small circle. And what is the definition of line segment PS? P is the center of the big circle. S is a point of the big circle itself. This is exactly the definition of a radius. That is to say, PS is the radius of the big circle that is equal to capital R. But we've already found out that capital R, the radius of the big circle, equals to 25 over 8. So we can write here that PS equals to capital R equals to 25 over 8. So, in conclusion, we found out that PS is the radius of the big circle, is equal to capital R, while QS is the radius of the small circle, that is equal to small r. So what is the length of line segment PQ? From the drawing, it is very easy to see that the length of line segment PQ is equal to QS minus PS. QS minus PS. QS actually, again, the length of this line segment PQ, it equals to QS PQ. It is equal to PQ. Here this looks like P. It looks like Q also. So here it is P. So here PQ, this line segment, equals to PS minus QS. PQ equals to PS minus QS. I repeat again. PQ equals to PS minus QS. So actually PQ, this line segment, equals to PS. We already found out that PX equals to capital R, so we substitute PS by capital R minus QS. We already found out that QS equals to small r. So in conclusion, we found out that PQ equals to capital R minus small r. But we already found out that capital R equals to 25 over 8, so we can substitute capital R by 25 over 8. We do it now, we get it in conclusion. PQ is equal to capital R, that is 25 over 8 minus small r. Okay? PQ equals to 25 over 8 minus small r. So we can write down here that the drawing that PQ equals to PQ, that is the hypotenuse of the right triangle QPM, it is equal to 25 over 8 minus small r. So actually, and what is the length, what is the definition of line segment QM? Q is the center of the small circle. M is the point of the small circle itself. This is exactly the definition of a radius. So QM equals to the radius of the small circle, that is to say, it is equal to small r. Okay? Now I'll copy the right main triangle QPM in a new page, and we'll implement the Pythagoras theorem in this right triangle QPM. Okay? So this is the right triangle QPM that I copied from the original drawing. We have already found out that the hypotenuse QP equals to 25 over 8 minus small r. We have already found out that PM equals to small r minus 7/8. And we have already found out that QM equals to small r. So this is the right triangle PQM, and we will implement the Pythagoras theorem here. PT is abbreviation for Pythagoras theorem, and according to the Pythagoras theorem, the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse here is PQ, therefore the square of the hypotenuse is PQ squared. And it must be equal to the sum of the square squares of the perpendiculars. That is to say, it must be equal to QM squared plus PM squared. I repeat again, according to the Pythagoras theorem, on the right triangle PQM, PQ square equals to QM square plus PM square. PQ equals to 25 over 8 minus small r. So PQ square is 25 over 8 minus r square. That is equal to QM square. QM equals to small r, so QM square equals to small r square plus PM square. PM equals to r minus 7/8. So PM square will be equal to r minus 7/8 square. So here we will open the brackets on both sides of this equation number 1, and we'll get that according to equation number 1, we have here 25 over 8 minus r squared. It is equal to, according to the algebraic identity, a minus b squared equals to a squared plus b squared minus 2 times ab. That is to say, this expression will be equal to 25 over 8 squared, that is 25 squared, that is 625 over 8 squared, that is 64, plus r squared minus 2 times 25 over 8 times r, and it is equal to r squared plus here r minus 7/8 squared will be equal to r squared plus 7/8 squared, that is 7 squared is 49 over 8 squared, that is 40, 8 squared is 64, minus 2 times r times 7/8. Okay. Okay. So here we have r square on both sides of equation number 1, so r square will get cancelled. And what is left from equation number 1 after we cancelled r square? What is left here is that in this side we have 625 over 64. Here we have minus this expression equals to minus 2 times 25r over 8. Here we will divide both the numerator and the denominator of this expression by 2, and we'll get that 2 minus 2 over 2 is minus 1, so minus 2 will get cancelled, and in the numerator we left only with minus 25r over 8. We have to divide 8 by 2, and we get that 8 over 2 is 4. So in conclusion, this expression equals to minus 25 small r over 4. And it is equal to r squared plus 49 over 64. Here we have the expression of minus 2r times 7 over 8. We will divide both the numerator and the denominator by 2. Minus 2 over 2 is minus 1, so minus 2 will get cancelled, and in the numerator we left only with minus 7r. And in the denominator we have 8, so we have to divide 8 by 2, and it will be equal to r. The 8 over 2 equals to 4. So in conclusion, we found out the expression minus 2r times 7 over 8, after we divide it by 2, it is equals to minus 7r over 4. Here we will multiply this equation by 64, equation number 1 by 64, and we get that according to equation number 1, here we have 625 times 64 over 64 is 625. Here we have to multiply by 64 minus 25r over 4. So it will equal to, here, minus 64 over 4 is minus 16. And we have to multiply it by 25r. So in conclusion, this expression equals to minus 16 times 25r after we multiply it by 64 is equals to minus 16 times 25r. In the other side of the equation, we have to multiply r squared by 64. R squared times 64 is 64r squared. Here we have 49 times 64 over 64 is 49. Here we have to multiply minus 7r over 4 by 64. So it is actually minus 64 over 4 is minus 16 times 7r. So in conclusion, this expression minus 7r over 4, after we multiply it by 64, it is equals to minus 16 times 7r. Okay. So if I got this equation number 1, so according to equation number 1, 625 minus 16 times 25r is minus 400r, and this is equal to 64r squared plus 49 minus 16 times 7r is minus 112r. So here we will add to this equation number 1, 400r we get that according to equation number 1, 625 and 400R minus 400R is 0, so we left only with 65. We left only with 625 on this side of the equation number 1, and it is equal to 64R squared plus 49, and we have here plus 400R. 400R minus 112R, it is equal to plus 288R. Okay. Here we will subtract 625 from this equation, equation number 1, and we get that according to equation number 1, 625 minus 625 is 0, and it is equal to 64R squared plus 288R. And here we have 49 minus 625, it is equal to minus 576. So here we'll divide this equation number 1 by 32, and we'll get that according to equation number 1, 64 over 32 is 2, so in conclusion this expression equals to 2R squared. Here we have 288R over 32 is plus 9R. And minus 576 over 32 is minus 18. That is equal to 0 because of the fact that 0 over 32 equals to 0. So in conclusion, we got the quadratic equation that 2R squared plus 9R minus 18 equals to 0. The coefficient A in this quadratic equation equals to 2. The coefficient B equals to 9, and the coefficient C equals to minus 18. And the variable that we are looking for in this quadratic equation is R, so X equals to R. And the general formula for solving out the quadratic equation is X equals to minus B plus minus square root of B squared minus 4 times AC over 2A. Here A, B, and C, they are the coefficient of the general quadratic equation, and X is the variable that we are looking for. In our specific quadratic equation, the variable that we are looking for is R, so we substitute X by R. So, and here we get that R equals to minus B. Here B equals to 9, so minus B is minus 9, plus minus square root of B squared. B equals to 9, so B squared is 9 squared, that is 81, minus 4 times A is 2 times C is minus 18. All divided by 4. Because 2 times 2 is 4. Okay, so here we have R equals to minus 9 plus minus. Inside the root we have 81 minus 4 times 2 is minus 8, and minus 8 times minus 18 is plus 144. So inside the root we have 81 plus 144, all divided by 4. So we actually found out that R, the radius of the small circle, it is equal to minus 9 plus minus square root of 81 plus 144 is 225, all divided by 4. So here we have two solutions that are possible for R. But first of all, here we got that R equals to minus 9 plus minus square root of 225 is 15 over 4. Okay. So here we have two solutions that are possible for R. The first solution for R is that R, the radius of the small circle, is equal in its length to minus 9 plus minus. Here the first solution is minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24, and minus 24 over 4 is minus 6. So we found out that R, the radius of the small circle, equals to minus 6. That is a negative number. But because of the fact that R is the length of the radius of the small circle, so R is a length, it must be a positive number. I will write it down here. R is a length, and as a length, it must be a positive number. It can never be equal to minus 6, that is a negative number, so we'll cancel the solution, and we're left only with the second solution, that R equals to minus 9 plus 15 plus 15 over 4. So minus 9 plus 15 is 6. So we have here R equals to 6 over 4. We divide both the numerator and the denominator of 6 over 4 by 2, and we get that 6 over 2 is 3 and 4 over 2 is 2. So in conclusion, we found out that R, the radius of this small circle, equals to either 3 halves, or in terms of numbers, it is equal to 1.5 units. And that is the answer to the question. Okay, R equals to either 3 halves or to 1.5 units. Okay, in the next step I will summarize the lecture. Okay. So actually, we have here a small circle that is inscribed by a semicircle, and we know that side CD equals to 3 units, side DB equals to 4 units, angle CDB equals to 90 degrees, and we want to find out the radius of this small circle. Okay? So first of all, we did a construction. We extended this semicircle to a circle, we extended this semicircle to a circle, and then we extended line segment CD by a straight line until it touches the circle at point E. So actually here CD is a straight line, and when we extended the straight line CD by a straight line, we got line segment CE. When you extend a straight line by a straight line, the result must be a straight line. So the result that is CE, it must be also straight line. So when I feel that CE is a straight line, and so if CE is a straight line, we have the rule that the sum of the angles on one side of the straight line is equal to 180 degrees. So if we focus on this side of the straight line CE at point D, then the sum of the angles at this side of CE at point D must be equal to 180 degrees. Okay? So which angles we have at this side of CE at point D? We have here 90 degrees and angle EDB. So here 90 degrees plus the size of angle EDB must be equal to 180 degrees, according to the rule that the sum of the angles on one side of a straight line is equal to 180 degrees. So here we subtracted 90 degrees from this equation, and we found out that angle BDC equals to 90 degrees. So angle EDB, this angle, equals to 90 degrees. So we know that angle CDB, this angle, equals to 90 degrees, and also angle EDB, this angle, it is also equals to 90 degrees. Okay? But when we completed the semicircle to a circle, we actually created another semicircle. This semicircle is a mirror image of the original semicircle. I repeat again, this semicircle that we created is the mirror image of the original semicircle, of this semicircle. And when we extended the straight line CD by a straight line, we know that this angle equals to 90 degrees and this angle also equals to 90 degrees. We actually created line segment DE that is also the mirror image of CD. Okay, and because of the fact that line segment DE is the mirror image of CD, they must be equal to each other in their lengths, and the only difference between those two line segments is between their direction. They are in the opposite directions. So, okay. So, we can write here that DE equals to CD by symmetry because of the fact that DE is the mirror image of CD. They are equal to each other in their lengths, and the only difference between those two line segments is their direction. Okay, actually they have a common point, that is point D, and they are in the opposite direction of each other, while DC is to the upwards, DE is to downwards. Okay? So, in conclusion, we found out that D equals to CE because DE is the mirror image of CD. So D equals to CD by symmetry, but we already found out that CD equals to 3 units according to what is given us in the question. So from this equation, phi equals to CD equals to DE, we will derive that DE is also equals to 3 units. Then, the next step, I presented to you a new rule that is actually rule number 1. According to Rule number 1, if two chords intersect with each other inside the circle, then the following equation is true. Here we have this circle, inside this circle we have chord AB that intersects with chord CD at point O. Point O is the intersection point. Point O is the intersection point of chord AB with chord CD. So if this is the data that has been given to us, then according to rule number 1, we can say that OE times OB equals to CO times OD. Okay? Again, AO times OB equals to CO times OD. This is rule number 1, so we can implement rule number 1 in our drawing. Why? Because in our drawing we have this circle. Inside this circle we have chord AB. This is chord AB that intersects with chord CE. This is chord CE at point D. Point D is the intersection point of chord AB with chord CE. I'll repeat again. In our original drawing we have chord AB intersects with chord CE at point D. Therefore, according to rule number 1, all the requirements of rule number 1 are met, and therefore we can write down that AD over DB equals to CE over DE. Again, AD times DB equals to CD times DE. I repeat again. We can write down that AD times DB equals to CD times DE, according to rule number 1. Okay? Here AD is the missing line segment. It is given us the question that DB equals to 4 units, so we substituted DB by 4. We have already, it is given us the question that CD equals to 3 units. We have already found out that DE is also equals to 4 units. So in conclusion, this side of the equation we have 3 times 3, that is equals to 4 AD. 4 AD equals to 3 times 3 is 9. We divided this equation by 4 and we found out that AD, the missing line segment, equals to 9 over 4. Here AD equals to 9 over 4. We actually know that any diameter is twice as long as the radius. And the diameter of the semicircle and also the diameter of the big circle is AB. So actually, if we divide the diameter AB to 2, we get the radius that is equal to capital R according to our definition. So our radius that is defined as capital R, the radius of the big circle, that is also the radius of the semicircles, it is equal to the diameter AB over 2. Okay? And what is the length of AB? From the drawing it is very easy to see that the length of the diameter AB it is equal to AD plus DB. Here AB equals to AD plus DB. If we divide it by 2, we get the radius of the big circle. That is capital R. We've already found out that AD equals to 9 over 4 and DB equals to 4 units according to what is given us the question, all divided by 2. Here we multiplied 4 by 4 and then we divided also by 4 in order to have a common factor with 9 over 4. So 4 times 4 is 16 plus 9 over 4. And we have to divide all by 2 in order to get the radius, of course. Here 9 plus 16 is 25, so 25 is divided by 4 and also divided by 2. So we moved 2 to the denominator and found out in conclusion that the radius of the big circle that is defined as R, according to our definition it is capital R, it is equals to 25 over 4 times 2. 4 times 2 is 8, so in conclusion found out that the radius of the big circle that is defined as capital R, it is equal to 25 over 8 units. Okay? Then we defined the center of the big circle as point P, and we defined the center of this small circle as point Q. And from the center of the small circle, that is to say from point Q, we drew the radius, we defined the radius of the small circle as small r, and we drew the radius QO that is drawn to the point of tendency. That is to say, the radius QO of the small circle, it is drawn to point O, that is the point of tendency D with this small circle. And whenever you have a radius that is drawn to the point of tendency, then the tendency D will be perpendicular to the radius OQ. Again, CD is perpendicular to OQ, that is to say this angle equals 90 degrees, and this angle will be also equal to 90 degrees. Okay, likewise, from point Q, we draw the radius QM. The radius QM of the small circle, it is drawn to the point of tendency, that is to say it is drawn to point M, that is the point of tendency of tangent DB with this small circle. And whenever you have a radius that is drawn to the point of tendency, like in this drawing, then the tangent DB will be perpendicular to the radius MQ. So DB is perpendicular to MQ, that is to say this angle equals to 90 degrees, and this angle will be also equal to 90 degrees. So we focus on quadrilateral OQDM. In quadrilateral OQDM, we have 1, 2, 3 right angles. Okay, here in quadrilateral OQDM, we have 3 right angles. The sum of 3 right angles is 90 times 3 is 270 degrees, plus the size of the fourth angle, that is actually angle OQM. It is angle OQM. In total, the sum of those 4 angles, they must be equal in total to 360 degrees, according to the rule that the sum of the angles in any quadrilateral is equal to 360 degrees. So here we subtracted 270 degrees from this equation and found out that the missing angle, angle OQM, it is equal to 360 degrees minus 270 degrees, it is equal to 90 degrees. So this angle OQM equals to 90 degrees, therefore in quadrilateral OQDM, we have 4 right angles. Any quadrilateral that has 4 right angles, we will relate to it as a rectangle. So quadrilateral OQDM is a rectangle, and we know that the opposite sides of a rectangle are equal to each other. So in rectangle OQDM, side OQ must be equal to side DM, according to the rule that the opposite sides of a rectangle are equal to each other. OQ must be equal to DM. But we have already found out that OQ equals to small r, it is the radius of the small circle. So from this equation, r equals to OQ equals to dm, we derive that dm is also equals to r. So here, dm equals to small r, this is the radius of the small circle. Okay, and what is the length of dp? Line segment dp equals to db minus pb. Again, dp equals to db minus pb. Okay, here dp equals to db minus pb. So dp equals to db equals to 4 units according to what is given us the question, minus dp minus pb, and pb equals to capital R. Why? Because line segment PB starts from the center of the big circle, that is to say from point P, and end at point B, that is the point on the circle itself. Okay, therefore PB is the radius of the big circle that is equal to capital R. So in conclusion, we found out that dP equals to 4 minus capital R. But we already found out that R equals to 25 over 8, so we can substitute R by 25 over 8, and we get that dP equals to 4 minus 25 over 8. Okay, so if here we multiplied, in order to have common factor with 25 over 8, we multiplied 4 by 8 and then we divided by 8, and we got that 4 times 8 is 32, so we have 32 minus 25 in the numerator, all divided by 8. 32 minus 25 is 7, and we have here 7 eighths. Okay? So dP equals to 7 eighths. Then we have what is the length of line segment. So we found out that dP equals to 7 eighths. And what is the length of line segment PM? From the drawing, it is very easy to see that PM equals to here, PM equals to DM minus dP. PM equals to DM minus dP. DM equals to small r. We already found out that DM equals to small r. While dP, we just right now found out that dP equals to 7 eighths. So in conclusion, we found out that PM equals to small r minus 7 eighths. Okay? Then I presented to you rule number 2. According to rule number 2, if two circles have an internal lunge between them, then the straight line that connects their centers passes through the lunge point of the two circles. So, what is the meaning of rule number 2? The meaning of rule number 2 is that if two circles have an internal lunge between them, exactly like in this drawing, the small circle is located in the big circle, and those two circles have an internal lunge between them at point S. That is to say, they are touching each other internally at point S. Point S is the lunge point between those two circles. So, if we know that two circles have an internal lunge between them, like in this drawing, then according to rule number 2, the straight line that connects their centers, that is to say QP, because P is the center of the big circle and Q is the center of the small circle. Therefore, PQ is the straight line that connects their centers together, must pass through point S, that is the lunge point. Okay? So, according to rule number 2, whenever you have a lunge point between those circles, then the straight line that connects their centers together, that is to say in this case is PQ, must pass for the lunge point that is point S. That is to say points P, Q and S are located on the same straight line, or PQS is one straight line. Okay? So, what is the length of line segment QS? The length of line segment QS, Q is the center of the small circle, S is the point on the small circle itself. And this is exactly the definition of a radius. That is to say, QS is the radius of the small circle that is equal to small r. Okay? And what is the length of line segment PS? P is the center of the big circle. S is the point on the big circle itself. This is exactly the definition of a radius. That is to say, PS equals to the radius of the big circle, that is actually capital R. But we already found out that capital R equals to 25 over 8. So PS equals to 25 over 8. Okay? And what is the length of line segment PQ? From the domain it is very easy to see that PQ equals to PS minus QS. Okay? PQ equals to PS minus QS. Okay? We have already found out that PS equals to capital R and QS equals to small r. The conclusion found out that PQ equals to capital R minus small r. But we already know the value of capital R, that is 25 over 8. So we can substitute capital R by 25 over 8 minus small r. Okay? PQ, the hypotenuse PQ equals to 25 over 8 minus small r. We've already found out that PM equals to small r minus 7/8, and QM equals to small r. So copy the right triangle PQM here, the green right triangle PQM in this new page, and implemented the Pythagoras theorem in this green right triangle. Okay, here the square of the hypotenuse equals to the sum of the squares of the perpendiculars. The hypotenuse is PQ, so the square of the hypotenuse is PQ square. And it must be equal to the sum of the squares of the perpendiculars, that is to say it must be equal to QM square plus PM square. PQ equals to 25 over 8 minus r, so PQ square will be equal to 25 over 8 minus r square. R equals to QM equals to r, so QM square will be equal to r square. PM equals to r minus 7 over 8 square. Okay. Then we open the brackets on both sides of this equation number 1, and found out that 25 over 8 squared, it is equal to 25 squared, that is 625 over 8 squared, that is 64, plus r squared minus 2 times 25 over 8 times small r. In the other side of the equation we have r squared plus r minus 7/8 square, and here r minus 7/8 square equals to r square plus 7 squared, is 49 over 8 squared, is 64, and minus 2 times r times 7/8. Okay, so here we have r square on both sides of the equation, so r square will get cancelled. And here we have 625 over 64. And here we divided both the numerator of this expression by 2. Because 2 over 2 is 1, so then 2 over 2 is 1, so what is left from this and from the numerator is 25r, and 8 over 2 is 4. So in conclusion, what is left from this expression is 25r over 4. And here we have r squared plus 49 over 64 minus 2r times 7 over 64. So we multiplied this expression by 64, and we found out that this expression equals to minus 7r over 4. This expression equals to 49 over 64. So we actually multiply this equation by 64, and here we found out that 64 we get cancelled, and we left only 625. Here minus 64. So here we left only with 625 after we multiplied the equation by 64. And here we have minus 64 over 4 is 16. So in the numerator we left only with 25r. We divided 8 by 2. In the denominator we have 4 only. Here 2 is cancelled, and here 8 becomes 4. After we divided it by 2. And we have we multiplied, we have here 49 times 64 over 64 is 49. And here we have minus 64 over 4 is minus 16. So this expression equals to, in conclusion, to minus 16 times 7r. Okay. Then here we added 400. Here actually 25r times 16 times minus 16 is minus 400r. Here we have 625, and we have here 64r squared plus 49, and 16 times minus 16 times 7r is minus 112r. Here we added 400r to this equation, equation number 1, and we found out that 625 equals to 64r squared plus 49, and we have here 400r minus 112r equals to 288r. Okay, so we have this quadratic equation, and we subtracted 625 from this quadratic equation. 625 minus 625 is 0. Here we have 64r squared plus 288r, and 49 minus 625 equals to minus 576. Here we divided this equation, equation number 1, by 32, and we got that 64 over 32 is 2, so it is a of 2r squared, and we have here 288 over 32 is 9, so 288r over 32 is 9r, and minus 576 over 32 is minus 18. So in conclusion, we got this quadratic equation that 2r squared plus 9r minus 18 equals to 0. In this quadratic equation, the coefficient a equals to 2, the coefficient b equals to 9, and the coefficient c equals to minus 18, and the variable that we are looking for in this quadratic equation is small r, so x equals to small r, and the general formula for solving out the quadratic equation is x equals to minus b plus minus square root of b squared minus 4 times ac over 2a. So we substitute x by r, because x equals to r, and it is equal to minus b. b equals to 9, so minus b is minus 9, plus minus square root of b squared. b is 9, so b squared is 9 squared, that is 81, minus 4 times a is 2, times c is minus 16, okay. So 9 squared equals to 81, minus 4 times a is 2, and c is minus 18, all divided by 2a. A is 2, so 2 times 2 is 4. So r equals to minus 9 plus minus 81. Minus 4 times 2 is minus 8. Minus 8 times minus 18 is plus 144. So inside the root, we have 84 plus 144. So r equals to minus 9 plus minus 81 plus 144 over 4. Okay. And here, r equals to minus 9. 81 plus 144 is 225. All divided by 4. The square root of 225 is 15. So here we have two solutions that are possible for r. The first solution for r is that r equals to minus 9 minus 15 over 4. Minus 9 minus 15 is minus 24. Minus 24 over 4 is minus 6. That is a negative number. But because of the fact that r is the length of the radius, of the small radius, r at the length, it must be a positive number. It can never be equal to minus 6, that is a negative number. We cancel the solution, and we have to only with the second solution, that r equals to minus 9 plus 15 over 4. Minus 9 plus 15 is 6, so r equals to 6 over 4. We divided both the numerator and the denominator of 6 over 4 by 2. 6 over 4, 6 over 2 is 3, and 4 over 2 is 2. So in conclusion, found out that r, the radius of this small circle, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. I repeat again, the radius of this small circle, that is to say small r, it is equal to either 3 halves, or in terms of numbers, it is equal to 1.5 units. Okay? Thank you very much.